Recall from chapter 6 that we talked about a couple of principles for quantum numbers. One of them was Aufbau's principle, which described orbitals being filled in order of low to high energy. So that's the reason why we have the order of the 1s2, 2s2 electron configurations. And then we also had Hund's rule that says half-filled orbitals of the same energy, or you fill up half the orbitals of the same energy before pairing the electrons in the orbitals. So you get all the plus 1/2 electrons before you start adding minus 1/2 electrons in a subshell. One of the things that valence bond theory is not very good at explaining is how something without half-filled orbitals can actually bond. So consider this molecule here, beryllium fluoride. If we looked at the orbital diagram for beryllium, we would see that it has exactly 0 half-filled orbitals. So how does it bond? See, this is the orbital diagram. It's got the 1s. It's got the 1s electrons. It's a filled orbital. It's got the 2s electrons. It's a filled orbital, and it doesn't have any space where it can actually share electrons in the same orbital. So how does it bond to anything? Well, this is explained through what's called the hybridization rule. So recall that the 2s and 2p orbitals are all available. In fact, all orbitals are available for all atoms. They're there, they're just not filled. And so what hybrid orbitals says is that in order to get half-filled orbitals, an atom can actually make a hybrid orbital by putting together one of the s orbitals with one of the p orbitals. And in fact, it can put one of the s orbitals, the 2s orbital, with two of the 2p orbitals, or one of the 2s orbital with all three of the 2p orbitals. And so what you do is you get a blending of an s orbital and a p orbital to form two new orbitals of the same energy. So it's kind of like putting s and p orbitals into a blender and then getting sp orbitals mixed up. That's what we call these new hybrid orbitals. They're sp orbitals. And so see how we're taking this one 2s orbital and one of the 2p orbitals, we blend it together, and now the new electron configuration for that atom is 1s2, 1s2, and then sp2, and then 2p. sp and then 2p. So it's got two of these sp orbitals. They're now half-filled and are able to bond with half-filled orbitals from other atoms. And so what happens then is you have these half-filled sp orbitals, so if you're blending an s orbital and a p orbital, what does it look like? Well, based on simulations that they've done on computers, the sp orbitals look an awful lot like a blending of an s orbital with a p orbital. If you blend these two together, they end up looking like this, where you have a little lobe on one side and a big lobe on the other. And then for the one of the sp orbitals, and the other sp orbital looks like a little lobe on one side and the big lobe on the other. But recall that these are always overlapped, and so the sp orbitals shown together look like this big giant p orbital. It looks an awful lot like the p orbital to me, always has. So now that we have these half-filled sp orbitals, we're able to bond with other atoms. So we look at beryllium here. We have this 1s and this sp orbitals. They're able to bond with the p orbital, the half-filled p orbital from, say, fluorine, and are allowed to do the BeF2 molecule. This sort of hybridization, where we form these sp orbitals, that is actually necessary. This hybridization is necessary for molecules with two electron domains, that is, molecules that have a linear geometry. And you'll find that all of the molecules, all the different types of electron domains, require these sp hybridizations. So if something has 3 electron domains around it, that means it has a trigonal planar electron geometry. What you have to do in order to get that sort of blending of that sort of geometries, you have to blend one of the s orbitals with two of the p orbitals. And if you blend one s and two p orbitals, you get three sp2 hybridized orbitals. If you blend, however, if you have 4 electron domains, in order to get 4 electron domains around a central atom, you blend one of the s and all 3 of the p orbitals, and you get an sp3 you get 4 sp3 hybridized orbitals. Notice that one s and p3, if you add those together, it equals 4, so you end up getting 4 hybridized orbitals. Also, you're putting in one s and 3 p's, so you always get out the same number of orbitals as you put in when you throw these atomic orbitals into the blender and get out these hybridized orbitals. So if you're to a Lewis structure, you can draw the Lewis structure, then you determine the electron domain around the central atom, and then you can just name it. If it's a tetrahedral, if it's got 4 electron domains, you can just call it sp3 hybridized. If it is trigonal planar electron geometry, you call it sp2 hybridization, and so on and so forth. And so these are just one more way of describing the electron geometries around that, keeping in mind that we have to have these orbitals. This explains everything up into sp3 hybridization, but what happens when we have to have 5 electron domains around a central atom? Well, if we have 5 electron domains, we have used up all the s, all 3 of the p's, but now the only unused orbital comes from the d. So we take an s, 3 of the p's, d, and we call it an sp3d hybridized orbitals. This allows for 10 electron domains around a central atom. And you see it ends up with that shape that we showed earlier for trigonal bipyramidal. If we go to s, if we add one more orbital, a hybridized orbital, we have to take the 1s, all 3 of the p's, and 2 of the d orbitals, and we end up with a total of 6 hybrid orbitals. We call this an octahedral electron geometry. And so these are essentially just one more way to talk about the type of electron geometry around the central atom. If it's sp, it's linear. It's a linear electron geometry, sp2, trigonal planar, sp3, tetrahedral, sp3d, it's trigonal bipyramidal, sp3d2, it's octahedral.